The last few problems that we're going to do are going to involve some techniques that we may not have seen before. They're pretty simple, just algebra manipulations that I just want you to know that you can do. You're allowed to do that. So, until you've seen it the first time, you wouldn't know to do it. But then once you've seen it, maybe you'll be able to start recognizing problems where it would apply. So, for example, number 4, we have 1 over 1 plus e to the x. Again, we might think about like, hey, a use substitution could be really helpful here. Okay, so a use substitution, if you did u equals 1 plus e to the x, then your du would just be e to the x dx. Now, we don't have another e to the x in the problem. So let's put one in. I think that's a great idea. Okay, so what I'm going to do is I'm just going to add an e to the x into the problem. Now you might say like, what, you can't just add e to the x wherever you want. Like that's not allowed. And you're right. You can't just add e to the x just because you feel like it. You have to balance that. So I'm going to add e to the x and I'm going to subtract e to the x. Okay, so I have not changed the problem at all because e to the x minus e to the x would cancel out. Okay. But what I am going to do now that I've done this is I'm going to split this into 2 separate fractions. I'm going to make this 1 plus e to the x minus e to the x, like that. Okay, see how I just split that up? Denominator is going to stay the same. And we're going to do that as 2 separate integrals. Now, super cool thing about this first one, notice those just cancel. This is just 1 dx. Minus, and then the second half of this one, remember that use substitution that we said we kind of wanted to use? Now we can. We wanted u to be that 1 plus e to the x, which made du up here, e to the x dx, which is exactly what we've got in the problem. So that's what we have. So now we're going to take the antiderivative of both of those. The antiderivative of 1 is just x, minus the antiderivative of 1 over u is natural log of u. And then we just need to plug back in. What was u again? 1 plus e to the x, that is always going to be positive, so I don't have to worry about the absolute value. And that's it. So that is a fantastic technique, is if you need something to make your u substitution work, you can add it as long as you balance it by subtracting it back out. Number 5 is also a natural log type problem. Okay. We have cotangent times the natural log sine x. This is going to be another use substitution. That's a very powerful tool for us. You might look at this and say, look, the function within the function is sine x. But if you do that, that makes du cosine x dx. We don't have a cosine x in the problem, so this is not a good selection for you. Okay. Now, that's still a u substitution problem, just not that one. Okay, so you might say, well, let's go bigger. What if we made u the natural log of sine x? The derivative of that, du, would be 1 over sine x, but that's a chain rule. So you have to do times the derivative of sine, which is cosine x. So that means du is cosine x over sine x. And trig identities, cosine x over sine x is the same thing as cotangent x. And that's fantastic because that's exactly what we needed. So remember, we said this was our u, and then cotangent x dx, that's our du. And now suddenly that's a very simple thing to take the antiderivative of. It's just 1/2 u squared. And then our last step is to plug our u back in, which was the natural log of sine x. All right, let's go ahead and knock out this last one. On the back of your formula sheet, or if you don't have your formula sheet with all the derivatives and antiderivatives, email me and I will send you another one. Or if you look in the front cover of your book, most of your textbooks had that sheet of derivatives and antiderivatives. On the back of that is all of your trig identities. Trig identities are going to be super useful in this particular problem. So again, we're going to probably start with the use substitution. It's a great tool. Our function within a function is 2x, which makes du just 2dx. We're going to divide both sides by 2. All right, so when we do that, actually let's stay in pink. I kind of like that idea. We get tangent squared of u, and then du, and I'm going to go ahead and pull that out. All right, so tangent squared, excuse me, tangent squared is not one of the ones on our formula sheet. Secant squared is, if you look at our integrals that we are on there. Oh, I have a great idea. Do you remember, let's get a different color here. No, how about green? Do you remember Pythagorean identities? One of your Pythagorean identities is something like tangent squared theta plus 1 equals secant squared theta. It's the second Pythagorean identity. So if you solve that for tangent, we get secant squared minus 1. So let's make that substitution. Instead of dealing with tangent squared, let's deal with this. So we'll substitute this in, and we get secant squared u minus 1. And then what I'm going to do is split that up into two separate things. Okay, so we have 1/2 antiderivative of secant squared minus, that 1/2 has to go to both of them, 1/2 of 1. All right, and now I think we're in a good place. Pop that up here. The antiderivative of secant squared is just tangent. So we have 1/2 tangent u minus 1/2. The antiderivative of 1 is u, and plus c. All right, now we need to plug back in for whatever our u's were. We have 1/2 tangent of 2x minus 1/2 times 2x. And last step, we get 1/2 tangent of 2x minus x plus c. All right, so some techniques that you can try as you're working through these antiderivatives in this section. I strongly encourage you to look at page 511 because I think it has examples of all of these types of problems that would use each of these strategies. Expanding the numerator, so sometimes like foiling it out. Separating the numerator, we did that in several examples on the notes here. Completing the square in the denominator, we didn't do that on any of these examples, but we did that back when we learned the arctangent one particularly, because you might be able to force it into an arctangent or arcsine, one of those. Dividing an improper rational function, you saw that using long division. Adding or subtracting terms in the numerator. Remember the problem where we added an e to the x and then subtracted it. Trig identities, we just saw an example using that. Or multiplying or dividing by a conjugate. That is also a really common thing, and maybe check out the book for that. So, like I said, nothing new as far as integration techniques. It's just using some of our algebra to manipulate these into forms that we can integrate.